quadratic equations. And the quadratic equations, we'll go ahead and see them in the lesson right now as we go in. But how do we exactly use quadratic equations to help us solve a real world problem in order for us to find some information that we need and we have given with information that we have given? So we've gone through our quadratic equations definitions to variable equations with the highest degree of 2. And here is our question for today. How can you use a quadratic equation, or how can you use quadratic equations to solve real world problems? Well, I'm going to go ahead and present you with a couple simple equations that we use, and you might see this in physics as well, but we're going to go ahead and see this here at a glance, not into deep how you would see it in physics or in a class like that, but at a glance where we were able to apply it to a real world problem or situation here. So the two commonly used quadratic models that we're going to go ahead and use, especially for or specifically for falling objects on the Earth's surface, is when we go ahead and represent our distance in fallen, basically what's the distance that we've fallen in feet and in time in seconds. So those are the two measurements that we're going to be using, feet and seconds. We're not including any metric or any other type of measurement that we're seen before. We're going to go ahead and just focus on feet and the time measurement in seconds. All right, so this is our first commonly used quadratic module or model per se for a falling object. And this represents the distance fallen in representation of time. And it's going to equal 16t squared, where t is given in time and d is in distance, right? Distance is in feet. So go ahead and copy this down on your notes because you will need this. D based on time, or distance based on time, is equal to 16t squared. All right, I'll give you guys 10 more seconds. Okay. All right. So our second most commonly used quadratic model that is used for falling objects, and this one's a little bit different because we're just taking a section of that fallen item, or whenever that item is being dropped. We're just interested of a little section. So if we're interested of a section, we're going to go ahead and do it again. Height in feet, and our time, or t, in seconds. And this time we're going to go ahead and have a height, which is represented by our initial height, our initial point that we're interested in looking at, minus that distance that is going to fall, right? So minus 16t squared, where our h sub 0, or h of o, is representing the initial height in feet. So this right here basically cuts a little piece of that trajectory that that item is falling. So imagine that I'm dropping something, but I'm only interested from when it falls initially, or when I want to take its calculation when it falls starting at one height, and then from a second height, right? Depending on just what is the height, or what is that time that it's taken for it to fall that time, that height. So go ahead and copy this one down to h of t equals h sub 0, or initial h, minus 16t squared, where h of t represents our height. Then we represent our h sub 0 in by its initial height. And of course, minus 16t squared, which will subtract that speed, right, or that rate that it falls. or basically that distance. So I'll give you guys 10 more seconds. All right. Let me go ahead and introduce you to your first example. Our first example here says write and solve an equation to answer the question. It says right here to give the exact answer, and if it's irrational, a decimal approximation to the nearest tenth is required, right? If you drop a water balloon, how long does it take for it to fall 4 feet? So go ahead and copy this down, guys. I'll go ahead and give you guys 30 seconds to copy this down, and then we'll go ahead and start solving this. But again, we're going to go ahead and give it an approximation and point out what items do we take in consideration and if there's anything that we exclude in here. So write and solve an equation to answer the question, give the exact answer. If it's irrational, we're going to go ahead and approximate to the nearest tenth of a second. And our question is, if you drop a water balloon, how long does it take to fall 4 feet? Now, here in this example, if you notice, we're not taking in consideration an initial height, right? We're not taking in consideration any section. We just want to know in total, how long will it take for it to fall 4 feet? So here's our balloon. It's not a water balloon, but still it's a floating balloon. If it were to just, drop from wherever it was dropped from um, we would be able to use our following model, right? Our following simple equation, which is our d of t equals 16 t squared, right? Where we have our d of t is going to represent the distance that it's traveled, and our t is going to represent its time, right? Now, in the question or in the statement that is says right here, if you drop the water balloon, how long does it take for it to fall 4 feet? So here in this case, we already know the distance, right? We want to know how long it'll take when it falls 4 feet. So our distance, our total distance is 4 feet. The time that it takes for it to fall 4 feet, we don't know. So that's what we're trying to figure out. Now, we know that our simple equation is d of t equals 16t squared. So we already know also that we're interested of it just falling 4 feet. We're going to go ahead and make d of t, which is 16t squared, equal to our d of t, which is 4. So let me go ahead and write this out. 16t squared is going to equal 4. Notice that they share the statement. D of t, our distance that is traveled. Here is our rate or that equation. Here is that distance traveled. Now, I'm going to go ahead and solve by using the square root method. I'm going to go ahead and do inverse operations. Divide by 16, divide by 16. I'm interested in getting rid of that coefficient of 16. I'm left with t squared equals 4 over 16. I'm going to go ahead and simplify it and write it as 1 over 4. Now from here, I'm going to square root both sides. And remember that whenever we take a square root, we now have a plus or minus, right? So here we have t equals plus or minus square root of 1/4. I need to do square root on top and square root below. All right, let me go ahead and continue to simplify. T equals square root of 1 is 1, so plus or minus 1, and square root of 4 is 2. So we have now our solution here. However, something that is very, very important to notice or state here is that because we're talking about a measurement or a unit that only exists if its positive values are taken in consideration. So have we ever had negative time? Have we ever gone back in time? unless we're in a movie. So we're going to exclude all negative values. So I'm going to go ahead and write exclude negative values, which means that this plus or minus will only be considered to have our plus. So therefore, our time for our water balloon to fall 4 feet will only be 1/2 seconds. Now I need to do nearest tenth. It can also approximate or equal um, 0.5 seconds. See, there you go. So we can go ahead and write our statement. A water balloon will fall for 0.5 seconds if it falls 4 feet. There you go. And you can go ahead and write your happy face that you proved it. So here we were able to use our simple equation, our d of t equals 16t squared. We know that the distance we traveled, or we wanted to know that, or we were told that it traveled is 4 feet. We are interested in knowing how long does it take. We substitute the two values or make them equal to each other. Then we simplify by doing the square root method. Again, apply the square root if we have a fraction on our right side. Apply or separate the square root on both numerator and denominator, and only take in consideration the positive value. Again, we cannot have negative time. We cannot go back in time. Therefore, we only take in consideration the positive time. All right, let me go ahead and save this. And you guys ready for the next one? Okay, clear. I can come back to this. I did save a screenshot of it, so we can come back to the other one. So example number 2, same instructions, write and solve an equation to answer the question. Give the exact answer. If it's irrational, a decimal approximation to the nearest tenth is possible. So the rooftop of a 5-story building is 50 feet above the ground. It says, how long does it take for the water balloon to be dropped from the rooftop and past a 3rd-story window at 24 feet? So go ahead and write this one down. And we'll go ahead and use our simple equations. All right, I'll give you guys 10 more seconds. All right. Okay, so let's go ahead and analyze the information. It says right here, rooftop of a 5-story building is 50 feet above the ground. And we have a little sketch right here to help us picture that out. So we have what we call a starting point, right? A starting point or a starting height. In other words, this is what we call the initial height. There you go. Height. What does this represent? Well, this is going to represent that h sub 0 or h above, or that starting or initial height that we talk about. Now, it's asking how long does the water balloon, once it's dropped, does it take to pass by a 3rd-story window at 24 feet? So we're interested when our distance is 24 feet, right? So we're going to go ahead and say that our d of t, that distance that we're interested, is 24 feet. So let's go ahead and see which of the two equations am I going to use. The first one that we had was our d of t equals 16 t squared. That second one that we had was our height that we're talking about. So our h of t equals that initial height minus 16t squared, right? So we have this somehow included. And I can go ahead and write this in here instead so that you guys can see it. So h initial height minus our distance, right? d of t, if it makes more sense. So we already know what this information is, right? It's that 24 feet that we have here. And by reading into our description, we are able to see that its initial position or initial height was that 50 feet, right? So here's our little man or a little person. Every time I look at this, I feel like they're gonna jump or something. But no, they're just throwing the, the water balloon, the water balloon off the top of the 50 feet or the fifth story building, the 5-story building. That water balloon is going to drop, and we're just interested to know when it passes this third story, which is at 24 feet. So our initial height, we can go ahead and say that it is 50 feet, that starting point. Now, we already know these two pieces of information, and we can go ahead and substitute our values, right? Now, let me go ahead and correct myself a little bit. This distance, sorry guys, the distance is not d of t. It's our h. We're interested in our h, sorry, the height. So the height that we're interested to know is when it passes 24 feet. Sorry, so this is our h of t. This right here is what we know as our initial height. So where it starts at 50 feet, right? Sorry, I apologize for that. So let's go ahead and substitute our values and solve for that beautiful time because we want to know how long, right? So our time, we don't know what that is. So let me go ahead and write h of t equals our initial height minus 16t squared. The height that we're interested, that we know that it's going to pass, is at 24 feet. So let's go ahead and substitute that. Our initial height was 50 feet. And we're interested to know about t. So we're going to go ahead and use now this quadratic equation. We're going to go ahead and solve for t. Let me go ahead and subtract 50. Again, we're using that solving by doing square roots. So let's go ahead and just leave our t isolated. Nope, not on the left side. Over here, I have 24 minus 50. It should give me negative 26, which equals negative 16 t squared. I have one more step before I do the square root. So I'm going to go ahead and divide by negative 16. Divide by negative 16. I'm going to go ahead and write t on the right side. Sorry, left side. T squared then equals, or you know what, I'm going to go ahead and leave it on the left side. Equals. So negative 16, let's see, sorry, negative 24, negative is positive. So this gives me positive 26 over 16 equals t squared. I can go ahead and do the square roots. Square roots. Let me go ahead and continue right up here. And I have now t equals, I can go ahead and separate my square root on top and bottom. Square root of 26, square root of 16. Let's see, 26, can we simplify that any further? I know that 26, if you do your tree, it is 2 and 13. 2 and 13 are already prime numbers. Nothing squares within it. So we leave it as square root of 26. And t equals, don't forget your plus and minus. T equals the square root of 26 over 16 square rooted is 4. So here we're only taking in consideration the positive value. So we're just taking positive instead of considering the negative. Again, it's talking about time, so we're only taking in consideration that positive value of the square root. So because we still have an irrational number, we can go ahead and give its decimal approximation. So since you guys have calculators in front of you, like Ms. Vasquez aware, you guys have a tab. T equals, let's go ahead and approximate that time in seconds. Square root of 26 divided by 4. What do you get? Anybody awake? Okay. Let me go ahead and bring my calculator out then. No, it's not 26 over 4. Let me go ahead and clear this out very quickly. And I'll bring it back. So we have square root of 26. It's equal to 5.09 and so on and so forth. All that divided by, I hate how it goes inside the parentheses or inside the square root. Let me go ahead and rewrite this. Divided by 4, it is 1.27. Let's go ahead and write that out. Back to my presentation, undo. So this would be what? Round it to the nearest tenth. If it's 1 point, or let's go ahead and say it's approximately 1.27 to the nearest tenth. It's at first, no, this is the nearest, yeah, this is the nearest tenth. So it would be, again, t equals 1.3 in this case. And we say seconds. So you can go ahead and write your statement. The balloon will take 1.3 seconds to fall from 50 feet to 24 feet. So that's when we're interested in a chunk. That's what I was addressing at the first, whenever I was introducing this part. So if a question is asking you to just take in consideration a little chunk of the trajectory or how that balloon is falling, this is when we use this equation. Whenever we're just interested in general, how long does it take for it to fall 4 feet, then we use that first one. So we just round up. So whenever we have 1.27, second, this is our 10th place. So this would be 100th. This would make this round up. So we write 1.3. Okay, just making sure everybody remembers that part. There's a lot of details that come in play, guys, that we just have to recall, and that's okay. Sienna just figured out that we can write on our screen. All right, everybody has this? Let me go ahead and save an image. You're wondering, like, what's happening? Yeah, I can save screenshots of the work here, and I can go ahead and bring it back. All right, ready for the last one. Example number 3. Okay, so the last one, guys, very similar. However, the two first equations that we gave you were for items that fall on Earth's surface, right? So let's take in consideration our gravitational pull and all that stuff. Now, this one here is talking about how items fall in the moon. So question says, on the moon, the distance in feet, and an object falls in time in seconds, again, the same units. is modeled by the function d of t equals 8 over 3 t squared. So suppose an astronaut on the moon drops a tool. How long does it take for the tool to fall 4 feet? So again, the equation is a little bit different. The idea is the same. So think about the first example that we had about the water balloon falling 4 feet. And we had our equation d of t equals 16 t squared. This time, because we're in the moon, we're in a different planet, or not a planet, different surface per se. It's a different equation, right? A different rate for it to fall. But the same concept applies. Let's go ahead and do this one. Let me go ahead and do this one in blue. Let's see. I have my tools here. Okay, so let's go ahead and see. We're interested on knowing how long does that tool fall 4 feet. So our distance, we're interested in knowing the time, and we're told that our distance, our d of t, in total is 4 feet. So how do we do this? Let's go ahead and substitute our two sides. D of t equals 8 over 3 t squared, and d of t also equals 4. So by substitution, we can go ahead and make both of them equal to each other. So let's go ahead and do that over here. 4 equals 8 over 3 t squared. And we're interested in solving for time. So let's go ahead and solve for time. Let's see. Multiply by the reciprocal, 3 over 8. Multiply by the reciprocal, 3 over 8. Eliminates my 8, eliminates my 3, right? So now I have 12 over 8 equals t squared. So here we already know what to do. Let's go ahead and take that beautiful square root of both sides. I'm going to go ahead and write my t on the left side and my square root of 12 and square root of 8. Now here we're going to go ahead and simplify. Before I simplify, let me do something else before I simplify, guys. Before I simplify, I'm going to go ahead and continue to take the square root. 12 divided by 8, I can reduce this. I can reduce by 4. Reduce by 4, I get 3 over 2. 3 over 2? Am I interested in doing that part? No, I'm not interested in doing that. I'm interested in reducing by 2s, not 4s. Like, Ms. Vasquez, what are you doing? It's strategic here. So divide by 2, divide by 2. I have 6 over 4. You must be wondering why. All right, so let's go ahead and continue to simplify. Here we have square root of 6 over square root of 4. Notice that this denominator, square root of 4, is going to simplify to 2. So we have plus or minus, let's see, equals square root of 6 over 2. And let's continue to simplify. Let's see, 6 is 2 and 3. It can't be reduced any more, so we leave it at it is. So our time here is, we're only taking in consideration the positive value, square root of 6 over 2. Now we can go ahead and give approximation, a decimal approximation, in order for us to get a more visual representation or a more accurate presentation on this instead of having that rational representation. So what would be the square root of 6 over 2, approximating 2 in seconds? You guys have your calculator. Okay, let me go ahead and bring mine. Let me clear, and I'll bring this back very quickly. Again, we have square root of 6. Let me clear. Square root of 6 over 2. And here it gives me 1.22. There you go. 1.22. Rounded to the nearest tenth. Notice that 2 is less than 5, so we're going to leave it at t approximates at 1.2 seconds. So how long does a tool take to fall 4 feet on the moon? It would take 1.2 seconds for the tool to fall 4 feet on the moon. All right, write your happy face. 1.22. Thank you, Jillian. All right. Any questions on this? Let me save a screenshot.